Hi, everyone, and welcome. Thanks for joining us for this informal, but what we hope you'll find is informative webinar on industrial CT scanning. I'm Victoria Russman, Creative Marketing Manager at PreTech. I'm joined today by three talented minds from our team. First off, we have Dave Nelson, owner of PreTech. He started this company over 30 years ago before CT scanning was cool. We also have Mike Heim, director of CT. He is an encyclopedia of knowledge when it comes to X-rays and material behavior. And then we have Carter Aldridge, CT specialist, who I'm pretty sure loves solving complex challenges using CT scanning. One note before we begin, if any questions come up throughout the webinar, go ahead and drop those in the chat. We'll hang on to them and we will answer all of them during the Q&A at the end. With that said, let's get into it and explore CT scanning. Dave, you're up.
Hey, again, thank you, Victoria. Again, my name is Dave Nelson, owner and president of PreTech since 1993. I'd like to thank everyone here for joining us for our very first webinar on 3D scanning with a focus on CT scanning. It's a nice alternative to our lunch and learn format. So if that's something that interests you, that's an event where we can come out, provide lunch, and deep dive into some of these topics. Also, since this is introductory, if anyone wants to deep dive into any topics, we'll take questions at the end, of course, and we can also visit with folks offline as well. So we've got an agenda today that introduces our company, talks about what is CT scanning and how it works, and deals with some of the very important topics that'll help you engage us for better outcomes, right? Resolution, accuracy, and some of the deliverables that we offer. Everything that you're going to hear today is geared at improving throughput. So kind of keep that in the back of your mind as we introduce some of the various topics. The whole idea is to get your product to market faster, recognize issues faster, solve problems faster. And that has brought us a few case studies. Unfortunately, due to the NDA nature of our arrangements with clients, we can't actually put product up here and talk about specific issues with our customer, but we have two case studies that were pretty dramatic. And in one, we were able to reduce the timeline from initial development to launch by about 7 months. And we brought CT scanning to bear on that project. And what it allowed us to do was visualize the initial condition of the mold, the tool, the part, and then start developing measurement routines in the backgrounds while the customer was out solving problems and making adjustments to the molds in the process. And so by the time they were ready to launch their product, we had all that measurement in place, and that executed in a matter of minutes, and that resulted in an enormous time saving and got their product to market. I was told in the area of about $60 million that they were able to accelerate. We had a major medical OEM come to us with 20 different tools being managed by one person, and we ended up launching that in about 16, 18 weeks, 20 weeks, and ended up saving that company millions of dollars in the process. And as a result, they went ahead and integrated the CT scan process into every area of the organization, R&D, quality, various engineers. So let me move right on and just kind of introduce who we are before we get into CT scanning. So we are, I talk about my people, my process, and my platform when I introduce ourselves. So we are coming from a metrology background since 1993. That's how we grew up. So we have years and years of metrology experience. Everybody that we hired for since the beginning has engineering backgrounds, engineering degrees, and our CT group comes from physics background with advanced degrees in physics as well as engineering. And we have a variety of software expertise from CAD software to measurement software to reverse engineering software and so forth. And so what does that mean for you guys that are going to engage us? It means you're going to have this high level collaboration. And I say collaboration because my customers are bringing their expertise to the table. We're bringing ours, and we're discussing project details, problems, and possible outcomes. And it just builds a lot more confidence, uh, in the outcomes. So we're trying to solve problems together. That's what that is. So process. We're accredited to ISO IC 17025, and I know there's a lot to that, but I generally highlight three different things that have been transformative. In the process of getting accredited, we have to define our measurement uncertainty. It's something we define, we test for, and we publish. And we need to have low enough measurement uncertainties to handle some of the precise tolerances that customers bring to us. Contract review, it's real simple. We go through, it's a box we check, and we review every aspect of your project to make sure that we have the capacity and the capabilities and the technical know-how to deliver what it is that you're asking us to deliver, right? So that's important because we don't want to have you go through the trouble of issuing purchase orders and sending us parts and then finding out later that there's some kind of shortcoming. Final inspection is real important. In the early days of our company, we were producing test reports that were laden with errors from time to time, right? So that's just the nature of dealing with the mass quantity of data. And we've really cleaned that up by making sure that every test report that goes out is signed not just by the person who did it, but it's been fully reviewed by a second person. And that eliminates everything from simple typos that might cause an aggravation at some point in the process to identifying inconsistencies in the data that warrant some kind of recheck. So those three things have been very transformative to us. And again, what that means to you is that you're gonna have a better assurance of accuracy. You're gonna have more reliable results. You're gonna have more confidence in the data. And that's not to say we don't make mistakes. We are humans. We still make mistakes. It's just that we have a mature process in place that mitigates a lot of that risk. Then we talk about our platforms, now, which we're starting to get interesting now, right? So we have traditional measurement platforms like CMM and vision systems, but we also use structured light or blue light. That's a technology that digitizes a part and all its surfaces, but it is limited by line of sight. So it's not going to be able to get necessarily down into deep recesses. There could be reflectivity issues, and but the uncertainties are comparable to other scan technologies, and for the right applications can be cheaper and more accurate. Computed tomography, CT scanning is what we're really talking about today. And this is an X-ray based technology that scans your part, creates a digital representation of that, but has the advantage of not being limited by line of sight. So we can see internal to the material, we can see assembly engagements, things that are hidden from the eye, and we can perform a whole host of post scan services, which include basic metrology, material analysis, defect, porosity. We can overlay the digitized version of your part onto another part or to a CAD model and get a visual idea of how your part is performing or how close it is to nominal. And so the benefits to you in acquiring full digitized scan data is that you're going to be able to visualize the condition of the part. You're going to be able to make decisions much faster. That information can be disseminated out to everyone in the organization so they can all be looking at it concurrently from their own job perspectives. That's a huge advantage. In the digital world, we can take measurements on the fly. We can make changes on the fly. It executes much faster. Any measurement routine that we have will typically execute in seconds, not hours or days like a traditional measurement equipment would. So now we get into the fun part. So I'm going to turn it over at this point to Carter Aldridge, who's going to introduce the CT technology. So,
like Dave said, my name is Carter Aldridge, and I'm going to be your guide on the science portion of this webinar right now. So, computed tomography or CT, it's been used in the medical industry for decades at this point, and it's starting to come over to the industrial side. And what it is, it's an X-ray based technology, and the key thing is it's going to be non-destructive, as well as providing full 3D images of both internal and external features. And what do we use it for? We can use it for pretty much anything. That's kind of the really unique advantage of this technology, is that if there's an application you think it could be useful for, it probably can, or we'll find a way to do it. But how it actually works is in most machines, this is going to be the typical setup. There's going to be some sort of X-ray source. That source is going to emit a cone-shaped beam of X-rays. They're going to pass through whatever the object that's being inspected is, and then they're going to land on a flat panel detector. And that part is going to rotate 360 degrees while the detector captures thousands of images. Just like if you've ever broken a bone and had to get an X-ray, it's capturing thousands and thousands of those 2D X-rays, and the software that can then go back and kind of compile all that into a full 3D volume. How we can achieve a greater resolution through magnification is by moving that object either further away from the source or closer to the source. You can kind of think of it as if, as a kid, you're at the movie theater and you wanted to put your hand up in front of the projector. Your hand's only several inches long, but if you put it in front of that projector really close, it's going to be 20 feet on that big movie screen at the end of the movie theater you're at. But resolution is obviously going to be a very important thing. It's going to determine the smallest feature that you can see on the part. And where we start to see this fall apart first is going to be on very small features and very small radii. So as you can see in the bottom right there, we have a nominal CAD image of this part, and it's kind of got this, perfect cubic grid pattern on it. But in the image above that is the CT data, and you can see that if we kind of lower that resolution, those sharp edges start to become rounded off, and that's simply just because we're not picking up enough data points or voxels. You can think of them as 3D pixels that the machine captures. And we can counteract that by increasing the resolution by, like I said, moving that part closer to the emitter so that it's casting a bigger shadow, if you will, on the detector. But by moving it closer, we're going to be narrowing our field of view. So we're going to be able to pick up less of an entire part, So we might have to just look at a certain area of interest or balance it out with, maybe a little bit lower resolution, but then we can capture the whole part in a single scan. And kind of to help visualize this, that flat panel detector, like I said, has a set grid on it. It's got a set pixel grid on it. And so in the left image, we can get high magnification by taking our logo, we're putting it very close to the emitter so that we're getting a big shadow on the detector. All of the data of the logo is being spread out among lots and lots and lots of pixels. It's going to be very, very, very crisp when it comes to the data that's being collected. But conversely, in that right image, the low magnification one, we've moved the logo further away. We can now see the entire logo. Nothing's cut off or cropped or anything. But instead of being essentially spread across the whole grid, now we're only on about, looks like, 8 pixels there. So we're going to be picking up a lot less crisp data from that scan. So optimizing resolution becomes a really, really important part of properly CT scanning an object. Obviously knee-jerk reaction, people, you ask them, what kind of resolution do you want? I want the best, And sure, I might be able to scan something at a very, very high resolution, but I'm only going to be picking up, maybe an inch by an inch area, which if you have a 10-inch part is not going to be good enough for you. So we try and counteract people overestimating how much resolution they need. And additionally, the closer the object is to the source, the less power the machine can use, which can start to increase things like X-ray artifacting, which is kind of, you can think of like, static on a TV. It's noise in the image. It also, like I said, it lowers that field of view, so we're picking up a much smaller area than we might need to pick up. And also conversely, if I do have to do a small area and I have to do several scans together to capture an entire part, that's going to drive up cost. We do always like to take a consultative approach and kind of work with you to figure out what will best suit your needs for each individual project. Now, kind of some examples of this resolution stuff that I'm talking about. I just grabbed a brass air chuck out of our back shop. It's a pretty common tool. Everybody knows what it is. But so we're going to look at some of the 2D X-rays here. And let's say we wanted to look at how these threads are interacting at the tip of the chuck. You'll see it says 25 microns for the resolution. And this is kind of an inverse thing. The higher the resolution, the lower the micron size will be. It basically just means that we're using smaller and smaller cubes to quantize the data. But as you can see at this low resolution, we see nice crisp lines along the threads. We can see how they're interacting. But as we move that part away and get a lower and lower resolution, we're starting to get fuzzier. Those sharp edges are becoming rounded. And, at something, at triple the voxel size, we're not really seeing what we needed to see if we were trying to look at those threads. But also, now not just a metal part, but plastic, we can kind of see how the resolution affects those small features that I was talking about. So we're going to look at the surface of this little toy tank, and at that high resolution, we can see this kind of these little features on the bottom side there. We can see all of the curves and radii and all the little bumps and all that. And as we increase that voxel size, you can see that little, greeble on the side there is going to get more and more kind of just uniform and just a blob instead of crisp like it was at the beginning. We're also seeing as we move further away from the detector, it allows the contrast to kind of equalize. So you'll see that the side of the tank is getting smoother as we get further away. It's because we were able to use a little bit more power, get a little bit better signal to noise ratio, and it's going to help smooth all that out. But like any technology, CT does have its limitations, that mainly being artifacting. There's several different types of artifacting. One of them is going to be extinction, and that's where the X-ray beam ends up being absorbed by the material and not making it all the way through to the detector. And so, you think X-rays, what's the thing that's going to limit that? The first thing that popped into our heads was lead. So we CT scanned this bullet here, and as you can see in that bottom left corner, we got this little, black patch where we know that there should be material there, but because the lead is absorbing the X-rays, they're not making it to that detector, and the machine doesn't know that there's something there. Another type of artifacting that we see is called beam hardening. We typically see this with higher density materials. In this sample, you can see how it's kind of bright around the edge and then fades to a darker gray in the middle and kind of has this undulating, I guess I'll say, a color or color intensity. And that's because as the X-ray beams hit that surface, the way that they scatter, the machine thinks that there's a apparent higher density on the edge of a material when it's actually a uniform material. Some more examples of the extinction. You can see these dark gray areas in this part here. This part is all made of the same material. It should all be that same grayscale value, but we're getting some extinction and we're seeing those big shadows. Here's a little bit kind of zoomed in image of that. And this last one is going to be what's called scattered radiation. You can see in kind of these large dark areas, those should be air. They should be black. But when that beam hits material, sometimes it doesn't continue on its straight path. It scatters. And so it's being picked up by a different area on the detector than the beam originally, came from or what material it went through. And so it shows up as this sort of fuzzy, snowy effect. There are ways to counteract all of these artifacting examples, whether that's through how the parts are fixtured in the machine to minimize the path length through the material so there's less deflection, whether that's using different pre-filters or energy settings, whether it's using some software after the fact to help counteract what we're seeing. Next is going to be accuracy. When CT first came onto the field, we had some customers that wanted to see how it compared to like a traditional CMM system that they were used to getting their results from. And to be a little bit nitpicky here in our laboratory, accuracy, it doesn't have a number. There's no unit for accuracy. I can't point at a CMM and go, that has 5 accuracy. That just doesn't make sense. But what I can say is that it has a certain uncertainty, a measurement uncertainty. That means that whatever the measured value that the machine spits out, plus or minus a set amount, the true value of that measurement has to lie within that band. And by looking at the uncertainty values, I can say that a certain device or machine is more accurate than another device or machine. But uncertainty is just kind of a mathematical way of addressing any possible error from a measurement. And as you can see, the posted values that we say for our CT machines they're accurate than most of the CMMs that we actually have in our lab right now. They're sitting at 5.3 and 9 micron, or sorry, 5.3 and 7.3. We've changed that recently. It's gotten better, microns. And, kind of a quick visualization of that, the CT is going to have a smaller band of uncertainty. That means that value is going to fall within a tighter tolerance than the CMM because it has a larger uncertainty. And the kind of neat thing about CT is you can actually, there's a visualization of that. So each individual voxel has its own uncertainty applied to it. So as you can see on the surface of this scan, it's kind of got this stippled orange peel type appearance. And that's because 2 adjacent voxels have different uncertainties. So one might be on the lower end, one might be on the higher end. And so you see this bumpiness across the surface. This does not affect accuracy in any way. It's just a visualization of that uncertainty. And we wanted to kind of prove this out. So I'll quickly kind of dive into this. This is a bit more of in the weeds nerd math stuff, but the machine comes with what's called a cupcake artifact. It's just helped to calibrate the machine. But it's a bunch of ruby tip styli like you would see on an CMM, and they're set up in a certain pattern, and we have known distances between the center of all of those spheres. And so we took those, we measured them on CT and kind of found the difference of all of those measurements from the nominal. And as you can see by the graph, another quick visualization, all of those, both the CMM and CT falling well within their posted uncertainty values, which would be that top green and purple line. But we also wanted to do it on something that was a little less uniform. So we took some parts, kind of ran the same thing, picked a couple dimensions off of the print, same deal, ran it a bunch of times, and we're still falling within those posted uncertainty values. There's a bit more variation just because there are parts that are coming from different cavities within a tool. They're coming from different processes. Each part, well, you want plastic to cool at the same rate. There are minimal differences between part to part to part. And lastly, again, we're just trying to compare the CT and CMM. So we're looking at some more of that data. But what does all of this mean to you? We want to assure you that the measurements and the volumes and things that you're getting out of CT are going to be just as accurate as traditional technology. And we want you to have confidence to make changes and make decisions based on the information that we're providing you. We don't want you to have any doubt, from the information that we're giving you. But now that I've talked about how you actually acquire, a 3T data set, at the end of the day, what are you getting? And like I said, there's so many different ways you can utilize this data. Kind of the first one that we do often is going to be STLs. It's going to be a surface wrap of the volume. This can then be used to do reverse engineering. We can take that into a software and start building out perfect parametric CAD models off of that. We've had clients that have obtained tools either through an acquisition or a merger or something like that were pre-digitized prints. They don't have any CAD models, but we can take the physical parts and help them build up their library of all of their products. And we can also take those and do first article inspections. We could check all of the dimensions on prints for you, CAPE studies, all of that kind of stuff. Into the more kind of unique things that CT can do, that's going to be porosity analysis. You'll see that in the bottom right image, and that's just simply looking for voids within a part. We had a little toy cinder block, like 3D printed cinder block, that we check for voids. We can do things like wall thickness analysis. We can do things like assembly failure. Finite element analysis, flaw detection is going to be very big. We do a lot of things you can see on the left bottom there. We do a lot of like crack detection and things like that, as well as in the top left as how different things are interacting within an assembly. Another big market for us is going to be color mapping. This is just really helps with visualizing what's going on with a part. We can take that 3D volume that we've scanned and we can either overlay it on a perfect CAD model, or we can even do cavity to cavity comparison if we're trying to look at something like how something ages or wears over use or over time. Some kind of more niche, unique things that we're able to do is going to be fiber composite analysis. It's very handy for fiber wrap cable or fiberglass inside of a plastic injection molding. It's just looking at how all of the fibers are oriented within a certain sample. We can also do foam and powder analysis. These are kind of yin and yang of each other. The powder, we're going to be looking at the distribution and size of the granules within the powder. And then conversely, the foam, we're going to be looking at the size and shape of the struts or the air gaps within the foam, I guess. This MyVGL viewer software is something that we provide to you. Volume graphics is what we use for a lot of those color mapping, as well as the flaw detection, the assembly interaction analysis, all of that kind of stuff. It takes the 3D volume, it's going to display it in 3 orthogonal 2D views. We can also set that up to be one of them to be a rotational view if the part's, diametrically symmetric, as well as it provides a 3D view in the bottom right. But this is just a very handy way of visualizing the 3D data. It allows you to, at your own time, parse through these slices, look at things, and make decisions on your own rather than just when you're immediately on a web meeting with us going over the data. So some of the benefits of these deliverables, visualization is the main thing. It allows you to see what is going on. As engineers and kind of R&D people, we're used to dealing with numbers on a spreadsheet. But being able to take, a color map and say, look, this part is warped here, to people who aren't as, deep into the science part of it like we are, it's much more intuitive to understand what is going on versus saying, this diameter is this value, this length is this length. Another thing is these are permanent records. We've had companies that, they upgrade all the computers in a department and they realize that they've deleted the data that we've sent them before. We hang on to this data indefinitely. You can always come back to us and we're more than happy to reprovide the data that we've captured for you or the analysis that we've done for you. And like Dave said, this just really just accelerates your time to market. It's all about helping you help yourself. One of the last things that we do is going to be those first article inspections. What you're seeing right here is this software used to be our main 3D analysis software for dimensional analysis, and this was based on old CMM data. It was, or not data, sorry, software. It was a CMM program first. So much like a CMM, it's taking discrete points, individual points on a CT surface, but at a much, much accelerated rate. I think this program has about 80 something dimensions in it. You can see it running here in real time. This is something that if I was to put this on a physical CMM, that would take upwards of at least a half hour per part, just because there might be, I might have to change the probe head. I might have to change the orientation of the part. I'm going to have to make sure that I'm doing a lot of clearance moves so that the probe isn't smashing into the part. But with the CT data, everything's digital. There is no, interaction with needing to worry about how something moves around something or anything like that, or flipping apart so that you can get access to different sides of it. Now we've moved on to mainly using Zeiss Inspect, which was previously known as GOM, and very, very similar software, but instead of doing the discrete points, we're now looking at entire surfaces. And instead of doing a part at a time, we're doing multiple parts at a time, and it's just increasing the speed at which things can be done. But at the end of the day, what does this all mean for you? We here at PreTech, we help to use our people, process, and platform, that power of visualization, as well as all the deliverables that CT can provide to help you fully integrate this into your workflow to save time, save money, and ultimately just get things to market faster. And we have a saying here, and that's going to be seeing is better than believing. Like I said before, someone who's a bit more engineering minded can understand, the numbers and the boring parts of our jobs, but being able to take something into, a meeting, a board meeting, something like that, and have people physically see what's going on and be able to intuit and quickly solve a problem, it's what we're here for. It's what our desired goal is. We do also have a kind of an ebook that kind of goes into a little bit more in depth everything that we've talked about here. But like Victoria and Dave said, we're here to answer any questions. So if there's been any that have been, typed into chat during the presentation, or if you have any now, we're more than happy to help answer those.
Hey, Carter. A question that comes up often, are there any size restrictions on parts for CT scanning?
Yeah, there is. We have two machines here in-house, a Metrotome 800 and a Metrotome 1500. The 800 is going to be the smaller machine. It has an envelope. I think it's probably do about 6 inches in diameter, and we can do, through stacking scans, we can do probably about, I think, 2 feet in that machine vertically. The 1500 is going to be a bigger detector. We can do about, I think it's 16 inches, and then we can do about 3 feet vertically.
So, we can add to that by saying there's some density limitations as well.
Mm-hmm.
These two machines that we're talking about are in the, energies are and machine configurations are, I'll call them metrology grade, but when we get into some of the higher energies, we can get more into strictly visualization. And when we go into those higher energy machines, we work with our OEM partners to provide our customers access to that. So we can go as high as 9 MeV. So we're, our 1500 was at 225 MeV or 225 kV. And we can get through, maybe quarter inch of steel.
We can get through like inch and a half.
Inch and a half of steel, maybe. And when you go up to the 6 MeV machines, I mean, you can punch through an engine block, get through, several feet of steel. So, through those partnerships, we're able to really kind of offer a full range of part sizes and densities.
So in addition to that, can you kind of expand on what materials might be restrictive, or materials that are typically compatible with this technology?
Yeah, obviously, plastic is going to be the easiest. We can get through a lot of plastic. It's very low density. And it's mostly tied into density. The more dense the material and more of the material is going to be the limiting factor. We typically like to mention steel because that's usually what we mostly see in production products. But yeah, much higher density materials, things like lead or depleted uranium or tungsten, those are going to start to be harder to get through, and we're going to be able to get through less and less material of those.
And then how about multi-material? Can you expand on that a little bit?
Sure. So there is a multi-material capacity with CT. Unfortunately, due to the nature of the technology, we do have to kind of err on the side of capturing the higher density material, which does degrade the quality of the lower density material. We do have some kind of software algorithms that we can do after the scan to help minimize any noise and stuff in the lower density material, but it won't be perfect. It'll still have a little bit of noise, but that's usually only in the 3D. If we're looking at 2D intersections, like in that MyVGL software, if we're kind of parsing through a part section by section, we do get much higher visual fidelity in the 2D versus the 3D for multi-material.
I would say stay tuned on that because we are acquiring some techniques that will allow us to have more control over the data sets. So we soon hope to be able to produce cleaner and cleaner data sets when it comes to mixed material. Separate those materials out a little better than we have been.
Sounds like another good webinar.
Yeah, could be. Could be.
All right. Well, if there aren't any more questions or any final thoughts, we can go ahead and wrap this up. I want to thank everyone for joining us, and thank you for your time. And I look forward to doing more of these in the future.
Thank you again, folks.
Yeah, thanks everybody.
All right. Have a good day.